So this week we're going to talk about air pressure, what it means. Uh, Interestingly, we've been doing surface maps a lot lately, and air pressure has been a part of that. So every time many of the labs you've worked on and all, and what I've shown you in different announcements and other areas has been about surface pressure. So what's the significance of it anyways? So first, every molecule that's out there exerts a force. In other words, there's a push on you all the time. Maybe that's why it feels tough to move sometimes because the molecules are hitting you so many times. But all molecules move at a certain pace, depending on temperature, their energy, all of it. And some molecules weigh more than others. So that force is what creates a pressure. Basically, it's accumulation of force of those collisions per unit area. In other words, if you had a 1 by 1 meter area and you took the forces that accumulate in that area from each little molecule in it, that would be total air pressure. Dalton, this guy did some work and discovered that, say oxygen has a given pressure, water vapor has a given pressure, carbon dioxide has a given pressure, nitrogen has another pressure. The total pressure of the atmosphere includes every single one of these types of air or types of gas pressure. So that's how it's defined. So it depends on both the mass of molecules, in other words, the more of them there are, and their kinetic energy. So in other words, if I had a place that had, 1 unit of kinetic energy, but I had 100 molecules in it, that would be a 1 times 100 area thing. However, if I had a area with 1 molecule but 500 kinetic energy or whatever, you get 500. So it depends on how many molecules and how fast they're moving. It's just also in where we live in the world we live on, weight is kind of the force of gravity exerted on a mass of air. Gravity weighs everything down. It pulls everything to the earth. It keeps us on the earth, which is a good thing. And through all of that, it creates an average sea level pressure of about 14.7 pounds per square inch. So every square inch on your body or on your building has a weight of 14.7 pounds on it. So why don't all these structures, all our body collapse inward? Because it's in all directions. We have air in us, we have air inside buildings, everything like that holds everything in place. How do we measure air pressure? Well, the very first measurement was taken by a mercury barometer. We don't use mercury barometers anymore because mercury is very dangerous, we've learned through the years. But all they did was take all the air out of a tube, like you had a straw and sucked real hard on it, and then popped that into the liquid, keeping the top on that tube. There's nowhere inside. The liquid will rise up that tube so many inches. And that is the weight of the air. So it's why weight began of the air or air pressure was always initially referred to in inches of mercury. Now we use things like aneroid barometers, which measure it differently. Another important fact, air pressure. While it is very nice to know what the air pressure is, the trend of air pressure is actually more important. In other words, if you have a low pressure system coming towards you, very first week of class, we said pressure drops when low pressure arrives. Well, that's how we use air pressure tendencies. If the pressure is dropping, maybe we do have a low pressure coming at you. If the pressure is rising, probably a high pressure. So that's why there's a continuous recording of air pressure. Literally through ASOS, every place there's an ASOS, we literally get a reading of pressure every few seconds. Here are some units of measure for pressure. The Pascal is basically what scientists use. So in other words, sea level pressure on average is 1013.25 hectopascals. There's another term for that in millibars. So 1013.25 hectopascals is identical to 1013.25 millibars. So on a weather map, you're seeing all these things in millibars. 1,004 millibars, 1,000 millibars. So what you're connecting is actually hectopascals, if you care. So air compresses the atmosphere. All right. If you had a bottle and put air in that bottle and put something on that bottle that would push the air together, you would be increasing the density, which increases the pressure. Now, in the atmosphere, that doesn't work quite so well. Why is that? Well, when you push on the air in the atmosphere, it kind of squishes out all the sides. So you don't do well that way. However, when you look at it as a globe and think about the gravity pushing down on the air, then the air can't squish anywhere. So it's compacted and gets tighter. More and more molecules are near the surface than there are further up in the atmosphere. We notice that when we breathe, when you go on top of a mountain, a lot harder to breathe than when you're down low. So all of that takes into account the fact that air pressure is going to be dropping very quickly in the first few kilometers of the atmosphere and then slow down as it goes further up. So here is an example of that, how you can see air pressure in the first few kilometers drops pretty quick and then really takes its time after that. So because of that, half the atmosphere by mass is actually below what we call 500 millibars, which is about halfway up, or 18,000 feet. So if you were on top of Mount Everest, for example, you'd be above half the atmosphere. And 99% of the mass is below 32 kilometers or 20 miles. If you think about that, if you ran a marathon in the horizontal, except you did it in the vertical, you would go through 99% of the mass of the atmosphere while you ran that race. So Colorado, for example, being a mile high, has an air pressure of about 83% of what Boston would have, which is at sea level. Here we've seen all these pressure maps. I've been having you look at them, showing you them. Here's the low pressure, here's high pressure, here's a gradient of pressure. So in other words, if I lived right here, we'll take West Virginia as an example, and if everything's moving from west to east, as the high moves away, my pressure is going to be dropping because the low is coming in. So that is what's causing a change in pressure. And you can see that right here on a graph of variations in air pressure. The faster the pressure drops, maybe the deeper the low is. The faster the pressure rises, maybe the speed of the high pressure coming in. All of that. And that influences the kind of weather we're going to have. All right. So the higher the temperature, the more there's kinetic energy in it. And we're talking about molecules that are outside now. They're going to move apart some. So even though the Earth is pushing them down, the fact that they get hot, like in the deserts, helps to push the air apart, makes it lighter. That's why in the summertime, for example, you'll see a lot of low pressure areas over deserts in the desert Southwest because of that fact. So First off, hotter air is less dense than cold air. It's very important. You're going to see a lot of that in the rest of this course. And that means that in cold air, the pressure is going to drop faster than in warm air. So if I were to give you a 500 millibar surface, which is halfway up, you would notice, we'll take the 500 millibar, we'll use contours. Contours are just the height of that 500 millibar surface above the ground. You will notice that areas where the air is colder underneath, the height of the 500 millibar is going to be lower and closer to the ground than where it's warmer underneath. In other words, if you went to the tropics, the 500 millibar will be higher. If you went to the North Pole, it'll be lower. All right, second fact. And this is one that's very confusing for many people. When I add humidity, the air is even less dense. So when you feel so humid and muggy outside, and it's so hot and humid, you don't feel like you want to move, the air is actually less dense than in the middle of winter when it's cold. The reason it's less dense, air mass, molecules of water vapor, weigh less than the molecules of normal air. So that you wind up with a less dense atmosphere, the more water vapor is in it. So cold, dry masses are going to be the most dense. They're going to have the highest pressures. Warm, humid air masses are going to tend to be less and have more low pressures associated with them. All right. The atmosphere is a fluid, so we've been talking about winds pushing or things pushing air together or pushing it apart. But if I push the air apart down at the bottom, if I were to spread my hands apart very quickly, you actually can feel air coming down, taking its place. The atmosphere doesn't want that to be in a vacuum there. So divergence is just molecules of air moving apart quickly. Convergence is air molecules moving together. So if I take them apart at the bottom of the atmosphere, they're coming together at the top, pushing the air down. So it's sinking. So if more air diverges at the surface than converges aloft, air is going to be less dense. You're going to wind up with pressure decreasing and a better chance of low pressure. So we talked about the fact that isobars are just lines of equal pressure. The reason we draw these at sea level is because we know that if we go up in the atmosphere, pressure changes, it gets lower, and actually gets lower pretty quickly, as we said. So I don't want a pressure that is from elevation. In other words, if I'm at the top of the Rocky Mountains, I might have a very low pressure. And if I'm at sea level, I have another pressure. But I want everything to be exactly on one horizontal surface. So that's why we put everything to sea level. We make adjustments to all these pressures so that they reflect if everything was at one horizontal elevation of sea level. All right, the ideal gas law. It says if I know pressure and temperature, I know density. Or if I know temperature and density, I know pressure. Everything is proportional, and each variable can change simultaneously to change the pressure. So the next step is there is work done or work by gas. For example, a gas moves up, it expands. If it expands, it actually does work when it's expanding. So what you've done, because it's doing work, some of the energy within that gas has done that work. So the temperature is going to drop. It's like if you open a bike tire, which is, it feel the air coming out of the valve, it's cool. Now, if I have a big cylinder like a tire pump or something else, and pump it up, you'll notice the heating on the cylinder on the walls you are providing energy to that air and warming it. So that's why air that goes up will cool, air that comes down will warm. So the internal energy gained by an air particle either increases the particle's internal energy or is used to do work. That's what we're talking about here. You can see it right here. With the air is compressed, energy is used, air expands, the air does the work. So with that, we actually can calculate how fast the air cools as it goes up in the atmosphere if it's dry. Notice I said dry. We know that condensation of moisture releases latent heat. So we're not going to want to take any account of that heat right now. All I'm doing is rising a nice dry air parcel. If you did that, it would cool at 9.8 degrees Celsius per 1,000 meters. So if I go up a mountain on a dry day, I am probably cooling at that rate. So the higher up I get, the colder it's going to get. And I can look at it and say, oh, I went up 3,000 feet. I'm about 15 degrees colder than I was at the surface. Now, if I do a moist adiabatic lapse rate, the key here is that you're releasing latent heat when you do condensation. Or when you have ice molecules, ice particles form in the cloud. So both of those cause the temperature not to cool as fast. Still cools, but not as fast. Notice it only 3 degrees now. So if I went up on a cloudy day with fog all around me, and I walked up 3,000 feet, I would only be about a little bit over 9, about 10 degrees colder. So that's a difference of 5 degrees. That can make, pretty significant difference on how I feel outside. So that's what we got here. And I just wanted to show you a quick weather map again. And here is actually pressures. We're going to look at them quickly because I wanted to give you an idea. This is Beckley, West Virginia. You can see here early in the week, pressure was fairly high, 1017. You can see it really rose up here in the middle part of the week, pretty good high pressure. Started dropping off again. Now it's beginning to rise up again. And you look at the surface map today, you'll notice there's a big high, 1038 millibar high to the north. Notice temperature is 43 degrees up here. That's a cold air mass. While there's a high down here at 1018, that's 20 millibar difference. And this air mass is relatively warm and humid. So that's why the pressure is lower. So now you've learned a little bit about pressure. Let me know if you have any questions about it.